Okay, thank you very much. I hope everybody can hear me, and I'm very sorry not to be there in person today. I'm afraid I had meetings on the other side of the country today, so I couldn't come to the meeting in person. So let me just get this started. So talking today about intelligent building management for a sustainable future, and just to give you a little bit of background about me. And my company. So I'm Joe Miles. I've spent 30 plus years in the building or construction world as a developer. I've run construction company, and Atamate came about 20 years ago because I was frustrated that I couldn't control buildings, particularly environmentally, from an environmental point of view, well enough. So control the mechanical systems in the building adequately. And the BMS systems were just, too expensive and actually not very flexible. And funnily enough, after 20 years, things haven't changed massively. And so here we are, and we're still doing what we're doing before. So Atamate is my technology company, and we call it Next Generation BMS. And, I'll be sort of referring to that as we go through. And then the Atamate Solutions is, we are also a mechanical, electrical consultant and contractor. So we're quite unusual in that we understand building physics. So we understand how buildings heat up and how buildings cool down, how you ventilate buildings and, produce hot water and such like. So by collecting this data, that's empowered us to sort of rethink a lot of how building, particularly mechanical systems in the buildings work. Just when I mention the word mechanical systems, just so everybody's clear, I'm talking about boilers, heat pumps, radiators, extractor fans, mechanical ventilation, heat recovery systems, and such like. So it's the plant in the building that does the heating, ventilation, keeps it healthy. That's the mechanical systems. I'll try not to use jargon as much as possible. I'll try and speak English. Okay, so what I'm going to talk about today is what is an intelligent building management system, and what I think it is, why it's not happening in the industry today, what an intelligent system would look like. And then to sort of lighten it at the end, I'm just going to run through some scenarios showing you real data coming out of buildings and, how that data helps you understand how the building's performing and how that data can make the building perform better. So that's the agenda for this evening. So kicking off with, what is a data-driven building? And really, this is how we see about it. It's collecting the right information, and the right information is predominantly going to be metering information from the building, and then it's going to be sensing information from the building. And that sensing information should be quite granular, so from every room, and you want to know things like temperatures, occupancy, possibly number of people, air quality, ambient light levels, possibly, all sorts of additional information can be useful, pressure, air pressure, noise levels, vibration and such like, and also collecting information from those mechanical systems. So more sophisticated systems like air conditioning systems and such like, you can link into and you can pull data out so you can understand if things like filters need changing or if they've got, problems and such like. So it's collecting all of that information and then it's processing that information. And I think that data really fits in three camps. So you've either got to use it in real time, and this is machine to machine use. And, the most simple version of that might be a thermostat, which we're all familiar with. And so, the temperature in a room drops and the thermostat then turns on the radiator and heats the room. The next sort of level on that might be to have some occupancy in there. So you say, actually, with the thermostat, don't turn on the heating until there's occupancy in there, and then turn on the heating. And that's the next level up. The next level on top of that might be to say, okay, here's the thermostat, turn it on when there's occupancy, but actually, if energy prices are very cheap, we could preheat that room at, very low cost in the expectation, because we know that it's going to be used later. So that's your kind of processing information. That's your real-time control. The next one's alerting. So alerting is really critical for the maintenance people in the building and the building managers. And they need to know, first of all, if there's a problem in the building. And so if if heater's not coming on, for instance, or a light's blown or something like that, maintenance information. And in the case of the building managers, they might want to know something completely different. They might want to know if the FM operative's actually gone into that room. They want to know if the security, if it's been occupied when it shouldn't have been occupied. You know, there's all sorts of things they want to know. But what's critical is they want alerting. And dashboards are a bit of a sort of myth in my view, because buildings move slowly. It's not like you're driving down the motorway at 70 miles an hour and you need to see the speedometer and you need to know if you're about to run out of petrol. With a building, you really want it to tell you when you need to get involved, and so that's alerting. Then the final use for the data is analysis, and this is the much more sort of longer term, collecting all the data together and then reviewing that data, and that's to sort of ask questions like, you know, it could be, does anybody use the meeting room on the 3rd floor, or you know, what's the heat loss in the extension, or these sort of bigger questions. And that's going to be much more of a sort of data churn exercise. It's sort of not real time. You know, how do we get rid of our gas boiler and go to a heat pump? You know, that's your kind of analysis data. So this is what, you know, I'd like you to sort of think about as we're going through the presentation in terms of, you know, the data that we're collecting and how we're going to use that data. So why is it not happening at the moment? And this hasn't really changed in my view for, you know, quite a number of years. And first of all, the existing systems are what I'd call siloed. So if you imagine that there's a project, let's say a school, for instance, and in that school, you're putting in a BMS system. So BMS system is a building management system. And this is the control system that predominantly does HVAC. So it predominantly does heating, ventilation, air conditioning systems in buildings. So you'd have a BMS system to control the HVAC. You might put a lighting controller on to control the lighting levels. You might have door entry, access control. You might have a burglar alarm, security alarm, and there might be some metering information. And currently, those are likely to be independent systems. I mean, some of them might be overlapping, but you know, it's not unusual to see them as totally separate. And each of those would require a specialist subcontractor to come in and install. And chances are each of those systems are going to have their own cabling that needs to be run across the building. So, and the final point to make is a lot of them need the same data. So if you're going to have a really efficient building, you want to know if there's occupancy in classroom 1, and you can use that occupancy sensor, you know, to control your heating and lighting and security. But currently with this setup, you can't share that data. So you end up with 3 occupancy sensors, one, you know, 3 times in that room to be able to detect that information. Sorry, wrong way. If you're lucky, that data will then go up into, they might have a supplier cloud, and that you can push that data up into that cloud where it can be, you can see it, but actually you still want to share data across, you know, really between the different systems. And so let's say that I want to have, it's a block of flats, and when I'm going to turn on someone's heating, when I see them come in from the street on the ground floor, and I want to use the access information to go to the BMS. Now, there's actually a arrow missing here. So potentially it's 2 routes here that you could either go, you know, directly from the access control, or you end up having to do this sort of very circular route, both of which involve quite a lot of programming and manipulation, you know, quite specialist, you know, configuring systems which don't generally naturally talk together, which broadly doesn't happen. And so, you know, that is the real problem with siloed data. You're not sharing data across the platform. Other issues I've already alluded to is you've got cabling. So this picture here is fire stopping. So most of the systems are currently cabled, and because they use bespoke cables, you're pulling cables across a building, and buildings are divided up for fire purposes into different zones. And every time you go through those zones, you need to make sure it's fireproof. So obviously, it's quite disruptive pulling cables around, particularly in existing buildings. I've already touched upon the problems with you need bespoke programming because you're interfacing systems which don't naturally fit together. And therefore, you've got specialist contractors who are going to be installing this stuff. And the other one that actually came as a bit of a surprise to me in business is how poor these systems are at cybersecurity. And this can be a real issue if you're looking to take data outside the building, because quite often they're running on PCs, and the only way you can do that is by opening the ports on the router, which is essentially a no-no for most customers. and consequently the data tends to be locked into the building and actually gets rewritten over the whole time. So all of these things mean that it's really cost prohibitive. And in reality, what that means is, except for the really sort of largest and most, sort of expensive, either prestigious office blocks or hospitals or big hotels and such like, you tend not to get a lot of data collection, and certainly not much joined up data collection across the building. And it's just because it's too expensive, in essence. And just to sort of finish this off, just to highlight this, if you look across different buildings, so you take housing, for instance, in housing, people don't tend to put controls in because there's no regulatory benefit to put the controls in. So even though controls are shown to save a huge amount of energy and consequently money, and they're probably the cheapest way to reduce emissions from domestic buildings, if you put controls in, you don't get a performance increase in your EPC, the Energy Performance Certificate, which is I'm sure you're familiar with it, which is how much energy the building uses, and therefore there's no incentive for landlords or the developers to put controls into those buildings. These sort of mid-sized buildings, so the school-type buildings, they really suffer from the siloed system, data security, and then when we get to the big buildings, obviously it's very expensive, it's complex, so they do put these controls in. They put the controls they necessary for it, but there's quite often landlord-tenant issues, and so what happens is that the landlord will install the BMS, but won't allow the tenant access to change the controls in their room. So if you imagine that you're renting, the tenant might be renting the 3rd floor on an office block, they won't have any access to the control in the building. And if they've got no one's going to work on Monday, they're working from home or whatever, they're still going to be getting the heating and ventilation and such like going into that space and paying the landlord, and they've got no control over it at all. So there are issues with these existing systems, and clearly, right across everything, retrofit is hard in all of these buildings. So what does good data collection look like? Well, you'd be surprised to learn it looks, you want a single platform in the building that you can collect all your data. So you're looking at pulling in all the sensor information, the metering information, the mechanical systems information, and potentially pulling in other information like pricing information and such like from the internet. All that data then gets pushed up into the cloud in real time, and that allows it to be stored and to be further processed, and then you can then share it with third-party systems. And so the example I've got there, CAFM, is computer-aided facilities management. So potentially one of the devices is reporting that it needs to have a filter change, for instance. That can get then pushed up, and it can get pushed directly into the CAFM system, and that will enable the contractor then to say, hey, look, I need to go, I can then timetable in someone to go and do that operation. Or it might be picking up that, it could be picking up essentially any sort of maintenance issues. And some of them could be picked up which are not directly coming out of reading out of one of the mechanical systems in the building. So just to explain that, if you've got a well-designed maintenance system, taking a relatively simple example, if you click a light switch in a room, the only person who knows lights have gone on is you. If you've got ambient light sensors in there, when you click a light switch, you can run a query on the database that says, hey, if I see a light switch click, within 1 second or 2 seconds, I expect to see a change in light level. And then if there's no change in light level, that can be reported into the system. And in the same way that you can do that with heating and ventilation and cooling systems and such like. So what you're doing is you're closing the loop in terms of maintenance information. So you actually now know that the end users, the building is performing as it's designed to do. So not only is it got to be holistic, we've got to join up all this information. The next thing, it has to be simple. So ideally, you don't want any bespoke programming. And ideally, you want to have the same config file, which is used in the building, that's used in the cloud. Because if you don't do that, then you're in a sort of world of pain where you're saying, I'm in room 27 and I want to read temperature sensor number 46, and I want to compare that to room 32, and and you can imagine it gets quite messy and complicated. So really simple. So all the data is properly labeled and easy to manage coming out of the building. You want it installed by electricians. So if it's just twin and earth, there's no specialist cabling. And then that obviously simplifies the whole installation process and removes the fast stopping problem that we raised earlier. and you're not pulling cables across the building, because you can always get a twin and earth, you can always get an electric power. It's relatively easy to get one of those in most rooms, in most buildings. It has to be simple to use. So simple to use varies, but to be honest with you, a lot of the time for end users, you're really just giving them switches and such like to press. So this thing in the middle is a wall sensor unit, and I'll come back and I'll show you some data coming out of those a bit later on. And I mean, this is a UI. Actually, these type of web UIs are not particularly useful for end users. So really, you're looking at buttons. Actually, we find work much better. And in a way, what we're trying to do is we're trying to turn a building into a robot. And what the building's doing is the building is always trying to do the right thing, and it's stopping people doing dumb things. So it's stopping, someone turning on the heating, turning out on the lights, and then leaving the room, for instance. But people like to have a semblance of control, and so it's important that they can change the heating settings, for instance, or control the ventilation or whatever it might be. So what we're trying to do is get a balance between the building sort of running itself and doing it as efficiently as possible, and at the same time making sure that people have control of what they need, so they're comfortable in their own environment, and that's the balance that we're trying to get the whole time. So, but it has to be simple. And finally, as I mentioned before, you need notifications. So again, real-time notification is quite useful. Getting it on a mobile device, again, is useful. So and so just to explain, the architecture that we put into our system. So we will typically put a sensor unit, which has got it's got 10 sensors in it, into most of the rooms in the building. You'll also you can link into all the existing meters in the building, but we can also put in a metering unit into the distribution board, so you end up reading individual circuits, so you get individual circuit level of information. You can add various other devices in, so we can put in relays and such like to control heaters. You can control air conditioning systems, and so and in fact in buildings there's really sort of 3 levels of control, if you like. So the first level of control, the most simple, is relays. So that's sort of turning on fairly dumb devices. So let me maybe dampers, opening and closing dampers on a ventilation system or something. Then the next level up is what we'd call a gateway. So a gateway is a translator between different technology standards. So you might be commonly in buildings things like BACnet and Modbus. So they're typically used, BACnet and Modbus are both commonly used in mechanical systems. So if you're talking to a heat pump or an air conditioning system and such like. And then the third level is an API level. So this is where you've got software to software talking. And this is less of this is in the building. I mean, sometimes you integrate it with more sophisticated things like fire alarms and security alarms or APIs. But typically, this is how you're communicating your data outside of the building, and you're pushing data into third-party software systems like a digital twin and such like, and sharing that data through that. So all of this data, so all these devices, so both the data collection side and the actuator side, that all use a Bluetooth mesh technology. So so that just means that if anything changes, then those signals get bounced around the building, and it's a very resilient and robust way to move data across the building. At some point, they get picked up into a local computer, which we call a hub, and there might be multiple of those in the buildings. And that really has 3 purposes. So the first purpose is it's got quite a high level of sort of cyber security on it. The second one is that it runs algorithms which keep this room at 21 degrees and 1,200 parts per million CO2 or whatever it might be. And the third thing is it pushes all that data up into the cloud, and it allows remote access to come into the let's say a estate manager and such like to go in, enter the building, so to speak, virtually enter the building, and let's say change the heating settings or something in the room. So that's how we approach it. So okay, so now sort of diving into how does building intelligence help sustainability. And I thought the best way of doing this was to give some show some data and show some examples. Actually, there's really 2 ways that we help sustainability. So the first is what we sort of call quick wins. So and I'll show you these first. These are pretty obvious coming out of the data. So using the data to turn off the heating when no one's in the space, that type of thing. The second way is a bit more subtle, and that's how you use data to inform how you're going to move the you're going to make changes to the building in the longer term. So it's a bit harder to sort of show those because they tend to be quite sort of more sort of report driven, more data intense. But we'll talk about some of those as we come through it. So just looking at real sort of basic stuff. So what we've got here is a time series of data. These big green blocks at the bottom are showing occupancy. So the occupancy is a combination of PIR detectors, like passive infrared detectors, which are like a security alarm type thing, or radar. So we use both. Sometimes they're radar, and then typically we're using carbon dioxide sensors, and we're looking at the decay of carbon dioxide sensors for knowing when a room's unoccupied. So we use the PIR, which is instantaneous, to turn things on, and then we use the decay in CO2 to decide that the room's unoccupied. So that's the occupancy at the bottom. Then we've got the heating as this red band, and then we've got the temperatures above. And what you can see is before the dotted line is that the temperature is just being held constant. So this heater, it's an electric heater, is just being turned on and off to keep that temperature constant. And you can see after this line, straight away we go into occupancy-based controls. And so you're allowing, when there's no occupancy in the space, you're allowing the temperature to drop back. And it's pretty obvious. It's relatively easy to start saving energy and saving money with that. So if we just add a little bit of level of sophistication on that, we come back onto our wall sensor unit. And now what we can do is we can have 3 set points in a room. And so, and this is particularly relevant in older buildings. In newer buildings or new build buildings, it's not so relevant generally because, I'll come back to that in a minute. But in older buildings, you'd have a setback point because you probably don't want to let the temperature drop totally, because it might drop down too far. You might end up with condensation problems in the building, and also it might take too long to reheat. So the building and different rooms in the building might have a different setback temperature, because if you're a flat right in the middle of a big apartment block, you're probably not, your temperature is probably not going to drop very much because you've got other apartments all the way around you. You've only got a small amount of external wall space. But if you're on the roof and you're on the corner in the roof, your apartment's sort of top left or top right or something like that, suddenly you've got lots of external walls and external roof, and therefore your temperature potentially drops more. So you maybe have a higher setback temperature. So what we're looking at here, these bottom lines here, so sorry, what I should explain, it's not very clear on here, but the square line is where we're setting the temperatures. And so, and I know it's difficult to see, but you can see that the sort of the almost like hand-drawn line, but the fuzzy line, I don't know what to call that, which I'm sorry, it's the same color, it's not ideal, but that is the actual temperature you've got. So what we've got is we've got 3 set points. So the first set point is when it's unoccupied, and that's this bottom line. The second temperature you've got is when someone goes into that space, then you go to the occupied line. And then the third thing you have is you have a boost temperature. So if someone's cold, you can go in and then you can boost the temperature, and that allows people to feel comfortable. And one of our sort of key objectives by doing this is to get rid of portable electric heaters, because we realize that if you don't give people the ability to boost, what you do is that they end up taking control themselves, and they buy portable electric heaters, and actually they leave them on, and they're much less efficient. And we'll come on to that in a while. So this is it's a balance about making people feel comfortable, and quite often building managers actually set relatively high boost temperatures because it's a way of appeasing your residents. And it doesn't only have to be domestic. I mean, we've actually used this in offices as well. So we used it in a whole range of different buildings. So I was going to say something else on this, gone totally out of my head, but yeah, okay. So yeah, hopefully that makes sense. But yeah, we do see really significant energy savings by using these devices. So this is just another example. So now what we're looking at here, again, obviously another time series of data, but we're looking at really granular. So these are different circuits in a distribution board. Actually, the cooling is misnamed. It's really a air conditioning, so it's an air-to-air heat pump. But what we can see is that when we turn on the heating control, there's a significant reduction in the green, which I don't know if you can read it, but that's the heating one. And actually, there's an increase in the air-to-air heat pump, which is a good thing because they tend to be a lot more efficient in terms of producing heat. So again, you can see you can see the same patterns happening both in terms of your sensors and on your metering. So it's not always about automated control. So sometimes it's about feedback to people. So this is the factory that we got involved in, and what we're looking at here is, you can see this is days of the month down the left hand side, and here's times of day, and the yellow color is when they're not using very much energy, and the brighter, the redder the color, the more energy they're using. And what's really nice here is you can see that the energy use is really constrained into sort of days of the week, so that you can see the weekend much less energy, days of the week, and during working hours. And so this is a really satisfying sort of example. And it didn't actually look like this when we first started working with them. And we found that they used to leave things like compressors on and such like over the weekend. So a lot of equipment was left on. And actually, through education, they improved the performance of the building significantly. So, it's sort of finding the right metric depending on the customer to get to reduce that energy, and this feedback's quite satisfying. Okay, so another sort of story. This is a town hall that we did, and that we found that in this town hall, the biggest use of energy was in the bar. So what we've done here, again, starting at the bottom, is that we've actually turned off lots of circuits. So you can see that there's no, most of them are grayed out. But what we're left with is bar equipment, which is the blue line, the lighting, which is the green, and then the socket load. And as you can see, that they're basically running, it's pretty constant during the days of the week, and they clearly have a party on Saturday night. And, so there's a bit more energy that's being used. So, but what's really shocking is when we start looking at the occupancy in this building. I mean, first of all, the occupancy is incredibly low. So, and what we've got here is we've got the lighter green at the top is the core hours of occupancy, which is between 9 and 6, and then the darker green is the out of hour occupancy time. So that's after 6, or between 6 and 8 in the morning, or sorry, 9 in the morning. So, and it's incredibly low use. Broadly, it's sort of, around 5% or less than 5% across the whole building, which is pretty shocking. And having done, quite a number now of local authority buildings, actually, this is not sort of atypical of many of these buildings, particularly historic buildings. And so, but what's even more shocking is when you go and look at the bar equipment, which we know is their highest load, it's only used 0.1% of the time. So basically, they're running it the whole time, and no one's ever in that bar. So that's an example of where it's quite quite obvious you had to go and turn it off. Also in this building, and this is monitoring before we're taking on control. What we're looking at here is we're looking at the temperatures when it's occupied and unoccupied. So the orange line at the top is showing the temperature when the room's occupied, and the brown line below is showing the temperature when it's unoccupied. And what we'd really like to see is we'd like to see the orange line always being longer than the brown line. So if we look at Market Hall, for instance, we've got a slight difference. It's 21.1 degrees when it's occupied, and it's 21 degrees when it's unoccupied. I mean, we'd like to see a much bigger temperature drop. But unfortunately, a lot of these rooms, like this office, sorry, that's all right. But I mean, if we look at, what's this room, the WCs or the ballroom, and ballroom here is 22 degrees when it's occupied, and it's essentially 24 degrees when it's unoccupied. So we know that first of all, we know that they're overheating it when it's unoccupied, and by going back into the occupancy level, we know that they're only using the ballroom a tiny. Where is the ballroom on here? Ballroom, it's only being used 2% of the time. So by putting some control in here, there's potential to save a lot of energy. And then generally, we find that we're reducing energy consumption in most of these buildings between 30 and 40% by collecting this data, identifying the problems, and then controlling the building more efficiently. So, and you can see on a building like this, I mean, 30 or 40% shouldn't be too much of a challenge. You should be able to do, way better than that with, its tiny levels of occupancy, essentially. So, This one I quite like. I mean, this one this is quite a fun one because the penny dropped with the guy who we're working with. So this is actually in a site cabin. So we do quite a lot of site installations and site cabins. And what we've got here is you've got this occupancy, you've got the heating on, the whole time. And then this bottom line is actually the outside temperature. And then this line is the inside temperature. And you can see that we've got where we would like to be heating to, and we're not hitting it the whole time. And when we explain this to the customer, they're like, oh, okay, this is the induction room. And the induction rooms on a building site are essentially where people get trained, and it's sort of in and out the whole time, and people always leaving the door open. So they literally went and bought a £5 door closer. They put a £5 door closer on, and the energy consumption dropped by about 50%. So it was really satisfying, it was really satisfying to people sort of got it, and a really small intervention made a big difference to the energy in the building. Okay, so those are some examples of quick wins. So just wanted to give you an idea of how you can put in relatively quickly and relatively simply. You can save quite a lot of money. I mean, one thing I should say is that in many offices, we find that people aren't working Monday to Friday, or Monday and Friday. They work, working from home on Monday and Friday. And so again, by just controlling offices, there's big energy savings available. This now is trying to understand how you're going to improve your building going forward, and in particular, how you move from gas and oil boilers to electrical heating, which is obviously critical part of the sort of net zero journey. And many organizations have got sort of targets to hit these figures in 2030, 2040, 2050 type thing. So what we have to start is we've got to understand why buildings use energy. And the first thing is the building form. So the building form is a combination of factors, but the first one is where is the building located in the world? And so building, clearly if it's on the equator, it's going to be different to if it's up in, if it's in Essex, for example. The second thing is that building shaded, or is it, in the sun? Is that building, has it got good insulation? Is it well insulated? Is it, does it have infiltration? It's got low level infiltration. So that's uncontrolled airflow through the building. These are all type of things which will impact how much energy that building will use. And so this is, this is well understood, and the form of the building. The next piece is how the building's used. And we've already obviously, we've shown you quite a lot of data. I've shown you quite a lot of data on that. And so you're beginning to understand, the use of the building is critical. And this bit is really poorly understood in essence. And people don't really appreciate just how important this is. But when you understand the building use and you understand the building form, then you can kind of specify what mechanical systems are going to be most appropriate to replace your existing gas and oil boilers. So that's the in essence, I mean, being fairly simplistic, but in a fairly simplistic way, you've really got three options when you're replacing your gas and oil boilers. Your first option is to go to an air-to-water heat pump, which is commonly called an air source heat pump. And the challenge you've got with those is that to run really efficiently, they typically want to run about 55-degree flow temperatures, whereas your gas boiler is probably running at 75-degree flow temperature. So the question is, and data can answer this, will your heating system still function properly if you're running at 55 degrees, or you've got to rip out your whole heating system and kind of start again? So obviously it's relatively easy to do. You turn down your temperature in winter, ideally on a cold day, and then you run it at 55 degree, your boiler's at 55-degree flow temperature. Then you can sort of understand if your existing radiators and heating system, whatever it may be, fan coil system, whatever you've got in the building, are man enough to heat the building, or whether you've got to rip out the whole lot and start again. Then the next option is typically going to be an air-to-air heat pump. So that's an air conditioning system, and lots of benefits around those. So that might be a more appropriate way to go to replace your gas or oil boiler. And then the final one is direct electrical. So direct electrical is either going to be electrical panel heaters, or it could be infrared. And again, in certain buildings, that makes a lot of sense in certain spaces. So quite often we put those in things like shower rooms, for instance, because infrared very good at heating up people. You also use them in things like garages, so in things like fire stations and such like, where you've got really high ventilation losses, but they need some heat, and you link it to occupancy. Again, it's a good solution. So that's the infrared. And electrical heating can be very appropriate where you've got a good thermal performance in the building. So if it's well insulated, the building, what you're looking for something is something that turns on and off very quickly and doesn't have a lot of thermal mass. So it will sort of cool down very quickly. It doesn't hold its temperature, because if you end up holding your temperature, then the only way people can hold the temperature constant in the room would be opening a window. So you'd want to avoid that. So essentially, this data can be used. The data we're collecting can really inform the most efficient way to upgrade the buildings. Now, I'm afraid I didn't have time to dig out any particularly good slides on this, so it's slightly, I just sort of dug out some other information. So first of all, I thought I'd just talk about power demand quickly. So what we're looking at is the instantaneous power needed in the building, and why this is useful is really if you're specifying solar panels and batteries. So by understanding where your peak loads are during the day or during the week, that can then inform you on where if it's appropriate and whether you're going to get a payback on it. And I mean, obviously, generally now we're seeing electric vehicle charging as being one of the biggest loads in the building. It's always a kind of, if we put solar on this building, are we going to get a payback on it? And does my solar, when I'm likely to get solar power, does that match when I've got a load? So obviously a really nice one would be something like a supermarket where they've got lots of fridges or, and so they're always going to need power. So, solar is a kind of slam dunk. Whereas if you go to an office or something, it might not be quite so clear cut. I just put in some information here. So this is another example of using data. I mean, this is a study that we've been working on with the university. I mean, it's a paper that's going to the CIBSE conference later. I think it's next year now. But we were just looking at comparing occupancy. So again, the information we're doing is we're looking in a variety of buildings. I've just put in students here and looking at how the occupancy in these buildings compare to the industry standards, which is NCM is the industry standard for commercial buildings in the UK, and ASHRAE is the American standard. And then, from that, you can start looking at, the heating and how much heat you're going to need and set points and such like. And then, you're comparing the load. So what I'm trying to sort of illustrate, and I sort of realize it's a bit late at night to be going into a lot of detail on this, but I'm just trying to say that actually you can start deep diving in this data and you can start getting a lot more information can come out. So, and here we go. This is the sort of final bit of that study, and it's just comparing the kilowatt hours in a month for the different models and compared to real data. Okay, so the final section of this talk, I just thought I would talk about some of the other elements on what benefits that intelligence brings or data brings. And broadly, we think there's 5 areas that we can really sort of benefit the building. So energy is clearly the first. We talked about that. Wellness, or particularly air quality, and I'll talk about that now. The third one's around maintenance and such like. The fourth is around security and things like door entry. And then the fifth is about sort of operations of the building. And you never quite know on the operations one. We're always surprised on how our customers use the data, because quite often they use data in a way that we just did not anticipate at all. So I've already touched upon air quality a little bit. So here what we've got is, again, I just have this slide handy, but it's what we're looking at is humidity. So the humidity difference between it's occupied and unoccupied. A similar thing for carbon dioxide. And then from that, you can start deep diving into a room. So yeah, so I'm jumping between buildings. I've sort of pulled these slides in from all sorts of projects, so it's slightly chaotic. Apologize. So here, what we've got again is our time series data. At the top, we've got the carbon dioxide levels. The next level down, we've got the humidity. Then we've got the temperature. Then we've got the occupancy again. And then down here, we've got fans. How often the fans on? So the more sort of dense the bars are, the more that those extractor fans are working. And then we've got this sort of before and after again. And so this is some flats accommodation. And you can see that, I mean, roughly speaking, so again, sorry, the top line of purple is when it's occupied, and this is now carbon dioxide levels. So we're around, I mean, that says 1300. that's 1400, 1400 sort of. So you get the idea, 900, 900. So it's around 1,000, parts per billion type thing. When it's occupied, and it's a sort of 700, 600, nearly 700, whatever, when it's unoccupied. So by controlling the fans based on air quality, you can see that straight away we've significantly improved the air quality in that building. So over 2,000 parts per million is not a great level of CO2. And on average, you can see it's dropped from around 1,000 parts or a bit higher to about 600 parts per million. So significant savings. Now, of course, that potentially comes with a cost because we're putting more air through that building. So that air needs to be conditioned and either heated or cooled, depending on time of year and such like. So, just to be aware that it's not, there's a bit more to it. Okay, this one I know is incredibly difficult to see, and so I do apologise for this, but it's an out-of-control GP surgery. So this is a building we went into. I just quite like this one because what we've got here is the blue is showing you the air conditioning when the air conditioning's turned on, and that's Monday, Tuesday, Wednesday, Thursday, Friday. And the air conditioning is basically running during the day, which is great. That's kind of when people are there. And then what we've got here with this green is the MVHR. So the MVHR is a ventilation system in essence. And what we're seeing here is that on Monday, it's not running at all. On Tuesday, it's not running at all. On Wednesday, it's running in the middle of the night. On Thursday, it's running in the middle of the night. Friday, Saturday, and Sunday, it's running in the middle of the night. So essentially, and this building had been commissioned about 3 years ago, and no one had noticed that the air quality was truly horrendous, basically, in these spaces. So, and this is a real major problem in the industry in terms of commissioning the building. And in my view, we should really be commissioning buildings for each season. So it should really be a quarterly commissioning because actually, buildings do change and you need to configure them. So, and no one had picked up on the fact that this building was not being ventilated at all. And in GP surgeries, that's particularly bad because obviously they've got sort of viruses and bugs and everything else, and there's a sort of term viral load. And a good proxy for viral load is the air quality. Okay, yeah, and here we go. This is sort of showing the same thing. So this is in the core hours, and you can see that the air conditioning is making up the bulk. And then out of hours, this is the MVHR, so all of the ventilation is happening out of hours. So there's no ventilation going on while there's occupancy in the surgery. So it's the type of thing that data allows you to pick up on quite easily. So I touched upon portable electric heaters previously. Portable electric heaters are a big issue because they're a fire risk, and also people tend to leave them on the whole time, and therefore most building managers ban them and they're not allowed. And we got a kind of rule of thumb in the company that if we see them in an office or we see them in accommodation and such like, generally you reckon that the electricity bill is probably 25% higher than it needs to be because sort of very, very, very sort of, rough guesstimate is that's how much additional energy that they're using. So if we start at the bottom, this is very similar. This is the same broadly as the chart I showed you before. So we've got the occupancy, we've got the heating when it's going on and off, and you can see it's hardly on at all. And we can also see that this is where we want it to be, but actually it's way above temperature the whole time. So, the question is, how can the heating be off and it's way above temperature? Well, the obvious answer is the portable electric heaters. So something's gone slightly weird with this slide. That's the occupancy again. So that matches that. So it's the same thing. And here we've got the data from the current meters. And you can see that it's dominated by orange. And orange is the socket load, essentially. So, this is a slam dunk that we've got portable electric heater in this space. And again, then we can send a notification to the building manager or whoever that can, raise a notification and they can go and sort the problem. Okay, so this is, I think this is my last slide, you'd be pleased to know. So I quite like this story. So again, this is on portable accommodation buildings, and this is on a big site. And I think it was a prison that they were building, and they weren't allowed to have the generators on nighttime. And they started getting all these complaints and saying, hey, the generator's on, it's running all night, what's going on? And they asked us to investigate, and we went and looked. And you can see the socket load during the day. So, that's where we are during the day. And suddenly at the night, it's ramping up. And, it turned out, with a bit of investigation, it turned out that the security guard was charging his car off the generator. And so it was turning on every night. And that's what was going on.